Hi, everybody. Welcome back. We're going to begin the next module, and we're talking about ideas around differentials for the next few classes. So these first two modules really are not yet about complexity per se. They are more about some of the underlying principles that will help you understand complexity dynamics once we get into them. So we touched quite a bit on rules, and in the end of the very last class, we were talking about kind of the space of possible executions of rules. So we talked about space grammars and how one of the things you could do is look at the sort of total space of all the possibilities of how a shaped grammar could be executed. So to better understand this notion of kind of the space of possibilities, I want to talk a little bit about topology, because this becomes a very interesting way of thinking about this sort of possibility space by looking at forms from a slightly different perspective that thinks about relations. Okay. So I want to start by just introducing a couple of key thinkers who are important people for you to know. The first one is Albrecht Dürer, who is an important Renaissance art, early Renaissance artist. He was working in Germany, and he did a lot of work tied in with perspective. He was also the first artist to do a self-portrait, which was very important at that time because it sort of expressed the idea that you could have subjects for art that weren't the royalty or the religious icons of the time. So in a way, a very humanist thinker. And he also thought a lot about the structure of different animals and entities that he saw in nature. And he looked at understanding these from a very contemporary perspective that we think about as differential thinking. The next figure is Darcy Thompson, and Darcy Thompson wrote a very important text called On Growth and Form, which was a text that I was introduced to as an architecture student. And his work actually is drawn from this much earlier work that was produced by Albrecht Dürer. So we want to take a look at these two figures, and then we want to relate this back as well to, or relate it forward to work that's happening right now in parametric thinking in design. Okay, so before we get in specifically to Dürer, I just want to first take a step back and think about how we tend to look at objects in the world or entities in the world. And if I ask you to think about a hand and to start describing what a hand is, in Western thought, we tend to focus upon the objects that make up something. So we look at the 5 digits and we say, well, a hand, it's made up of 5 things, and then you've got a palm. And we put pieces together, but we're looking at the pieces, we're looking at the objects. And this is a common way of thinking, and it's one that we really sort of take for granted. But it's interesting to try to flip that thinking on its head and think, well, is there a different way in which we could begin to define what a hand is? Think about that for a second. So let's suppose that instead of thinking about a hand in terms of 5 objects, we think about it in terms of it being constituted of 4 relationships. So here it sort of is a subtle shift in thinking, and maybe there is no obvious advantages of thinking about it this way, but it begins to change how you frame what a hand is. So you have these digits. This relationship is a different kind of functional relationship from the relationship that I have between these 2 fingers. I can stretch differently. There might be relationships of extension too. You could sort of start to think about one as being longer than another, so having a different ratio in terms of how it's functioning in your hand to do certain things, to execute certain activities. So if we begin to frame things in terms of relationships, it does a slight altering shift in how we imagine what things can be. And there is more and more sort of understanding in biology that the way that nature thinks about what a hand is more to do with the relationships than to do with the objects. So let's take a look. In evolution, you have these different kinds of animals that have hand-like skeletal structures. So you have wings, you have claws, you have paws, you have hands. And the way you could think about this is that in each of these, you have kind of a common sort of general blueprint, But then the relationships between the objects within that blueprint keep on being stretched and distorted and contorted. And that brings about different kinds of functionalities for these different entities, where we have these differential outcomes of the kind of structural features being activated according to the differential forces that these different kinds of hand type things have to be responding to. So if you're flying, you've got a different kinds of forces that are shaping what that's going to be, whereas if compared to if you're walking, compared to if you're hanging. And according to these differential forces, the relationships begin to alter, and you start to create new kinds of skeletal structures and bone growth according to natural selection. So these skeletal transformations, we can relate to this idea of topological transformations. And topological transformations are basically the idea that you can take a given entity and stretch it and pull it and contort it, warp the relations within that object in order to generate new kinds of figures. When you think about the world in this way, then it becomes composed of far fewer general sets of sort of primary objects, because the same primary object, when we see in this illustration, for example, we have a pyramidal shape with a hollow inside, that can transform into this other shape that doesn't really look like the pyramid. It looks like it's a very different form, but it is the same form, just stretched and contorted differently and smoothed and rubbed. So there's a joke that topologists have, that a topologist is someone who cannot tell the difference between a coffee cup and a donut. And we're going to watch a little video about that particular joke.
This is Topology joke. This is a joint work with Keen and Crane. So there's an old joke in topology. So a topologist is somebody who can't tell the difference between a coffee mug and a donut. So topology is the study of geometrical objects when you don't care about lengths and you don't care about angles. All you care about is a sort of global shape properties. And so everything's made out of very stretchy rubber. And in particular, that means that if you take a coffee mug, you can sort of unindent the place where the coffee goes, and you can kind of squish out the handle a little bit, and eventually you can deform it into this fully symmetrical round donut shape. So as the joke goes, the topologist doesn't know the difference between these, because in the study of topology, you don't care about any of these actual geometrical shapes of these different objects. As I say, this is joint work with Keen and Crane. He actually designed the shapes of these. I just did a little bit of editing to make them printable. Where do the shapes come from? Well, the thing you want to think about is soap films. So if you have a soap film, perhaps not in the shape of a coffee mug, perhaps in the shape of a bubble, and you poke on it a little bit, or you blow on it, then it gets out of shape, and then it tries to snap back into this sort of minimal energy. The surface tension of the film tries to minimize its energy and change the shape so that it takes up the least area. And so there's a sort of energy that it's minimizing. And the same thing is going on here. So Keenan started with this shape of the coffee mug, and then all these complicated features and sort of not terribly symmetrical shapes have a high energy in some measure, in fact, something called Wilmot energy. And then you flow in the same way that a soap film tries to reduce its energy. You flow around to these more and more symmetrical, less high energy shapes until you get down to this shape, the perfectly symmetrical torus, which is the minimal energy thing that you can get to. And that's sort of analogously, that's where the soap bubble wants to be. So obviously these are made out of ceramic. This is at the time of recording, this is a new process from Shapeways. It's not currently publicly available.
Okay, so he talks about some interesting things. I think it's a good illustration of what a topological transformation is. And he also talks about it in relation to this idea of kind of a shape wants to go back to its minimum energy form. And in the case of the coffee cup, its minimum energy form would be the torus shape, because that's the most sort of relaxed version where you can't sort of minimize the differences anymore. There's no sort of transformation that it could go through that creates sort of less space between the elements. And I can illustrate that here. I mean, another topological form would be this ball. And so a torus cannot transform into this ball because this ball doesn't have a hole in the middle. That actually involves piercing or puncturing a topological form, and that alters the topology. But the ball can become this shape here, right? And we can see that this shape here is actually, you could imagine that if I had taken that ball and I had sort of poked in and kind of held these ridges into it and forced it back, I could change the ball into this shape. But I would be doing it in a way where it kind of almost wants to bounce back. It wants to relax back into that sphere shape. So he talked about the soap bubble as being a good analogy. And you can imagine that a soap bubble doesn't want to be in this shape. It doesn't have the minimum energy. So topology is interesting. And it starts to reduce the kinds of objects that are out in the world. Instead, we can talk about objects and how they can be stretched and distorted into other shapes. So going back to Dürer was interested in this topological space of all possible faces. And so he wrote a book called The 4 Books on Human Proportion in 1528. And in it, he studied faces, but he studied them not in terms of individual features, but in terms of relationships between features that could be stretched and distorted and skewed. And according to how these distortions occur, you would be able to create all the faces out there in the world. So let's take a look at what Darcy Thompson did this. 400 years later, Darcy Thompson took a look at a fish, and using the same principles as Dürer, he looked at different species of fish, but he sort of laid them out on a grid, and then he would shrink the grid or stretch the grid or warp the grid and try to see how the same basic fish shape really was, depending on how you distorted it, would then morph into all the species of fish that we see out there. So this becomes a very interesting experiment, but it's based on this work of Darcy Thompson, where he's sort of pulling and stretching these parameters in different ways. So I want to take a look. I've uploaded on the website a toy for you to play with that allows you to play around with topology. Obviously, nowadays with computation, it's very easy to create these kinds of grids that Dürer and Darcy Thompson worked with in an interactive way. But we're going to look at a quick interactive tool to see how we can play with this. Okay, so here we have this Dürer transformation tool, and you can see that I can click on any of these dots and begin to drag them. And we begin to see that the face is composed of, rather than thinking of it as being composed of a series of features, that it's really these relationships between the features that begin to distort the face. The other thing we can do is we can pick up a corner and we can pull it in different ways in order to skew the face and begin to explore sort of this space of all possible faces by simply moving these parameter bars. You could think of them as parameter bars. That's not how Dürer would have phrased it, but I think in sort of modern computational lingo, these would be parameter bars that we're stretching. And with only a few parameter bars, we wind up having a very rich array of faces that we can explore. So play around with that after class, and we'll continue. Okay, so Dürer also looked at this in terms of the optics of monuments, because he realized that if you're looking at a monumental plaque, and you have the same size of text at the top of the plaque as you do at the bottom of the plaque, then the text at the top is going to appear as smaller. And so you needed to make some alterations, some distortions in the perspective in order to keep the perceived text size similar, regardless of the height it is on the monument. If you're stationed at ground level over here, you're standing way down low here. So what are your sight lines in order to make the text appear to be of a similar ratio? So he looked at that both for text, but he looked at it as well in column etchings and trying to understand how you could create etchings in columns that would optically maintain a consistent distance. So if you look at this arc over here, if you're standing in the center here, the spacing is equal, but it distorts the spacing as we move up the column line. And what I want to do is to compare this work by Dürer in 1493 to the work of Skidmore, Owings, and Merrill in 2014, both designing columns. And just to illustrate how much Dürer was ahead of his time, that the same kind of distortions that SOM is using in sort of a parametric column design that's stretching and altering as you move higher up, Dürer was playing with these same ideas before computers back in 1493, simply using graphic tools to try to kind of understand how you could play around with these sorts of stretchings and distortions. So the other precursor that that Dürer, I feel Dürer is a precursor to is the Sims, because if you've played around with Sims 2010, you know that you can slide around these parameter bars similar to how we slid around these bars, and we can kind of start to stretch eyes and make things, ratios between the elements different. But this is all about looking at the ratios. It's all about looking at the ratios between things instead of looking at the things in and of themselves and altering those things. And so it's a very, very different way of thinking about manipulating form. And this is the kind of manipulations that we are seeing more and more when we get into parametric architecture. In parametric design, what you're effectively doing is you're setting up a series of relationships, and then you're playing around with alterations in those relationships. So you use a tool that is effectively a relational generator that is composed of various inputs that then have a formal output in Rhino. So here we can look at these as the inputs, and these are like an X, Y, Z input. And we can think about those. Say we have a figure that relates to, it's going to be a rectangle, that there are certain sort of object primitives. And we have a rectangle, and we say, so the input for the rectangle is related to these three parameters. And we could have something that is strung into the X parameter that says, if this number changes, change the input of the X, or change the input of the Y parameter, or change the input of the Z parameter. So there can be an external input that leads into what's controlling the X, Y, Z parameters of the formal output. But let's just take a look at what some of the formal outputs would be if we were sliding these things around to different values. So we have X, Y, Z, the height, the width, the depth, right? And we can make something skinnier, we can make something squatter. We're basically taking the same figure and we're doing a series of topological transformations to stretch it in different ways and yielding different outputs. And we could do this very randomly, or we could say, well, you know what, I look at this and I say, this is something when we have a higher population than over here. Say this is, I don't know, an office building. And so this is obviously a higher density office building than something that's just one story high. So we could be, say, controlling for the height of the building based on a different input that sort of says, well, if an input of population growth is staying at a certain level, then we go to a lower value. And if population is growing at a certain threshold, then we input a higher value for the X, and that's going to cause it to be a higher value of the building going up. So that is one way to sort of think about these parametric controls, is that not only do you have a generator, but these generators, you could slide those things any which way. The question is, which way do you slide the sliders? And that can be based on some kind of input from the outside world that you say, well, this is the situation at hand, so we're going to modify the parameter bars in this particular way. The other thing is that in addition to getting these sort of shifts within a topology, sometimes you can jump into a new topology. So say there is a conditional moment, like I'm down here, right, and I'm stretching this figure further and further and further apart. I might eventually hit a threshold where now I've gotten to a floor plate that's just too big for me to not have some sort of internal courtyard. So beyond a certain value, maybe I say, okay, now I've got to introduce a courtyard into the space. Now I'm into a new topology. I can still stretch, distort, do something else with that topology, but I've kind of gone beyond a certain threshold, and so I move into a different form. Or I might say that I'm going to play around with the corners and have a parameter where these things start to curve, and maybe a curling building will sort of happen depending a little bit on how the neighbors are curling. So the intensity of the curl will be based on what would be a good one? Maybe traffic speeds. And so the traffic speed would be sort of an internal input that then controls the arc of a curve of the buildings that are on more frequently used streets. So there are all these kind of conditional rules that are coming together in a parametric model. And I just want to give you an example of this, of how these relational generators are able to produce this kind of formal output, how this is activated. I know the first time that I saw parametric design, I was sort of very blown away by just the unusualness of the graphic qualities that were being produced. And as part of what I want to do today is demystify this a little bit for you, so you can just see, okay, well, what are actually the mechanisms that are happening behind the model? And that in a lot of ways are not very different from what you're going to be playing around with when we're just sort of moving those parameters of the face and twisting it back and forth and getting all this kind of variety generated, where basically the model is exploring the topological space of possibilities that is then sort of tweaked and stretched in different ways to explore that space. So I'm not going to show you this entire video. It's based on a project that from the AA in London. The project starts off by saying that in the first 4 minutes or so, it outlines how the model is based on different kinds of scenarios. So they imagine a scenario that's more about tourism, another one that's more about very fast economic development. And so that is kind of what is controlling the values of what you put into some of these X, Y, Z parameters. And then these values, they form recursive chains. So I should go back to this last slide. As a value changes, as an input changes here, it affects an output, and that output then becomes the input for the next piece, et cetera, flowing through. So if you make one change in the system, it has a cascading effect through the entire system, because these rules are kind of relationally oriented. In the same way that when we looked at relational rules and it said, don't have a building that is in Seattle, don't have a building that's 1.5 times larger, the street frontage, than the building next to it. You could have a relational rule so that as a width of this expands, if this is the neighboring building, it's constraining how large that building, the width of it might be, okay? So let's go, and we're going to, I'll pause me and we'll watch the video. Okay, and so here we are. He's just talking about the different kinds of potential scenarios for this town.
The tourist destination will have a mix of mid-rise hotels and malls, along with low-rise resort-like developments along the coastline and waterfronts, and this scenario would lay significant weightage in public transportation as well, due to heavy intracity movement. The satellite scenario will be low or mid-rise urban sprawl with heavy intracity movement, implying high vehicle ownership and thereby wider roads and more parking spaces. This scenario will have the least emphasis on public transportation or pedestrianization. All of the cities in UAE are coastal cities, which makes them very linearly stretched in one direction and only a few kilometers deep in the other. The urban area of Ras Al Khaimah is 30 kilometers long along the coast and only 4 kilometers wide in the other direction. The site is selected just north of the estuary, stretching across the entire width of the city. As it is located in the heart of the city, it gives the opportunity to demonstrate the urbanism in 3 varying geographical conditions: the coastline, the desert edge, and the estuary edge. The site is presently very sparsely populated by a few plotted residential developments, leaving major stretches of land for future developments. A proximity-based analysis is done on the site based on parameters like major road intersections, pedestrian walkability, optimized locations for transport nodes, waterfront, existing development, and road network. These values are sampled on a point grid across the site by a system of urban programmatic distribution and zoning. The system is controlled by a graphical user interface representing the 3 scenarios as a triangle, and the position of the user control point inside the triangle determines the blend between the 3 scenarios. As the user moves the point in the interface, the system adjusts programmatic distribution values in real time, accentuating or dimming down the significance of the geographical proximity values sampled. The system also manipulates the coastline, maximizing it or leaving it untouched depending on the scenario. There are sliders to control growth or proliferation, which can be linked to the financial health of the city, where an economic collapse would mean minimal proliferation. The second slider changes the output of the system in terms of the map type, which can change from programmatic distribution to FAR and flow plate areas to programmatic mixity or connectivity. The connectivity map identifies transportation nodes based on walkability zones and also produces localized street patterns within these zones. Each one of these maps remains directly linked with the scenario interface, so they change in real time as the scenario changes. This system gives the possibility of controlling the entire urbanism through an interactive system that can be directly linked with the market economy and its financial trends. These maps are linked with families of generic urban massing typologies common in contemporary cities. Each produces a different spatial or formal character when distributed across an urban field with morphological variation of FAR and open space. Some are designed to formally resemble existing sprawl-like development. Some are designed to minimize surface area in the hot desert climate, or form large continuous open spaces while others fragment them. Some others work very well with long linear streets. Some can produce very high density or work well within a hexagonal grid, or produce perimeter blocks with courtyard-like spaces. All of these typologies are designed to seamlessly morph from one state into another in all states of density or open space. When linked to the system of urban zoning and programmatic distribution, they are capable of producing entire cityscapes only by adjusting values in the triangular interface. The tourism scenario maximizes the coastline and places most of the significant development next to a waterfront. The business district scenario gives an equal importance to road networks and coastline and produces high-rise, high-density development where it finds an optimal combination of both of these parameters. The satellite town scenario assumes most development to be lower or middle-income residential in nature and therefore places them away from the coast and closer to the road networks and desert, leaving the premium land for future development as is the present state of the city. The intermediate state blends between the scenarios, determines the influence of each and respectively tunes the formal variation, as well as the urban parametrics like FAR and open space structure of the development. The system produces entirely different cityscapes for the three extreme scenarios and blends between them when an intermediate value is chosen. The resulting urbanism ranges from extremely dense high-rise megastructure-like developments to low-rise high-density developments, or a mix of both, or low-rise low-density urban sprawl.
Okay, so I hope that after watching this, it's easier to see how some of the amazing kind of complexity of the graphics that we're seeing in this parametric approaches are really at the most basic, simple analysis, the same as just doing those stretches with a couple of parameters that we saw with Durer's faces. It's just a more sophisticated version of the same principles at work. I want to think a little bit about this is a way of composing space, and you can think about it as a notion of correlation, where we're looking at relationships and how these correlate, versus composition. And effectively, you are determining those correlations by how you are setting up your formulas in an Excel spreadsheet, because really all that Grasshopper really is a kind of visualized Excel spreadsheet where you're sort of saying, well, if this number goes up, then raise this other number by a certain ratio of the first cell. And so you can think about that as a very interesting way to generate design. I guess the question that I would have and that I would ask you to ponder is really whether the output is just because it's been sort of tabulated within a computer, whether that makes the output relevant. Because sometimes you can say, okay, well, if we've analyzed everything and if we put all these parameters in, it somehow makes it more objective in some way. But really, the relevancy of the design is contingent upon the usefulness of the underlying algorithmic assumptions. So if we are making the wrong assumptions about what should we do when a certain number goes up, we have to put that into a formula. We have to say, well, let's assume that when population goes up, we will shift to this kind of high-rise architecture. Those kinds of assumptions at some point have to be made by a person who's inputting those formulas into an Excel spreadsheet. And then there's a question of whether the insight is there, even if we can sort of explore this field of possible futures, explore these topological spaces of architecture, whether we're making the right assumptions in terms of how we explore them. So I find that parametric architecture is very cool. I think that if you're interested in this kind of design, you may want to take a look at some of the coursework that Nick Sensky is offering. I guess the question becomes whether or not this is really complex in terms of my interest in complexity, which is more about how things can evolve over time. Because certainly in this example, we can explore a lot of possibilities of spatial configurations based on data. But at some point, we have to make a commitment to say, okay, of all these topological possibilities, we're going to build this. And then the question is whether this is the right thing on the ground or not, or whether it can evolve over time. All right, so we will continue on with the next part of this. Thanks very much for your attention.